All right, well, why don't we go ahead and get started? As I mentioned just a minute ago, my name is Paul Craig. I'm the principal developer of the EFTC modeling, EFTC Explorer modeling system. And we will be discussing today some of the new features that are available in the latest release the latest release of EEMS 8.4. So the content here today is intended to be roughly about 30 minutes of essentially presentation with about 30 minutes approximately of hands-on demonstration of the tools, so we can show the dynamic nature of these tools and how they can quickly be used. When that last section is finished, we will have opportunity to have a question and answer period for up to 30 minutes in the Q&A session. However, during the actual presentation or during the hands-on, if there is something that needs to be clarified or I'm not clear and you have a question, you can ask a question online to Tom Mathis. You can put a question, type him a question, or raise your hand, and he'll let me know, and then we can stop and answer any particular question that has need of being answered during the actual presentation. But I will, if it's just a general question that you might have, we can wait to the Q&A session at the end. So with that, let's go ahead and talk about some of these new tools. So I guess many of the current participants on this webinar are actually unfamiliar, or at least very early new users of the EFTC Explorer modeling system. So we'll have a little bit of intro to EEMS, but then the rest of the content is focused specifically on the habitat analysis capabilities that we have added to EEMS with 8.4. So we're going to be looking at particular features are the new critical limits analysis feature, and then the habitat suitability criteria feature. And these are both just basically post-processing features, capabilities to EEMS that sit on top of a developed 2-3 dimensional hydrodynamic model that of the domain that you may particularly have of interest that you're studying. So we'll be looking at a number of different parameters, and I'll discuss that, but the examples here are predominantly just using the velocity and depth, which are the standard IFIM, PHAB, SIM parameters that are often used for these studies. But with EFTC Explorer, the new extension here is that we now can do these types of analyses for just about any parameter that is being simulated by the model that you're using to drive the habitat analysis. We're going to be specifically looking at a couple of species and then different life stages of those species for both the critical limits analysis and the habitat suitability criteria. So just in the way of kind of introduction, we're extending with these habitat tools. We're utilizing the in-stream flow incremental methodology, or IFIM approach to do some of these analyses if you desire, but this is an optional approach, and it's just the way you set up the underlying model. as to whether or not you're actually simulating, say, a real condition that exists in your domain, or you're setting up some user-defined but not necessarily realistic flow regime in order to do this, the IFIM approach. And then what we're talking about with EEMS 8.4 is we've extended essentially the PHAB-SIM approach, which is, simulation of the physical habitats when we're looking at microhabitat changes and their effects on flow and other processes that affect the habitat of a particular species. So now, as I said, that we can extend it to temperature, we can extend it to dissolved oxygen, sediment bed, the nature of the bed through using the channel index value, and all of this information is brought into EEMS, and then it can be saved and reused very easily. So that's a brief overview of the habitat capabilities, or the habitat analyses that EEMS now supports. So just looking at the tool itself, the EEMS tool, as you can see here, the link to our website is available right there, and we'll go to that a little bit later during the hands-on session. So what is a EEMS? It's essentially this holistic framework where you can start here at the top of this little diagram, where you have your environment, your domain of interest. You can build your grid. You then load that into the EFDC Explorer tool, and then you incorporate all of these data that are available for the site to build up the model and all your boundary conditions. You run the model, which is the EFDC plus three-dimensional hydrodynamic model. Output from that is then post-processed by EE into various reports and analyses, and one of those analyses now is the habitat analysis. So just a different way to look at that same information. From the diagram here is you have at a core, you have this pre and post processor, EFDC Explorer, pulling in all this different diverse data, processing and generating the necessary files to produce input to the EFDC model, which then when it runs, it produces output, and EFDC Explorer reads that information, does the analyses, and has a lot of tools to help calibrate and conduct these analyses. And this can be an iterative process, as indicated by the arrows. And just some of the tools for pre-processing and post-processing, and again, lots of information available on the web. So with that, let's jump into the demonstration model. This model, by the way, is available on the website. You can download this example and run these analyses yourself if you so desire. But this is the domain on this top left panel here. It's a river domain with upstream inflow at this end, and this is the downstream end to the right. Flow is moving across the domain from the upstream to downstream. And then we have the grid shown down here, so you can understand roughly the scale of the grid. And the grid's about, because this is quite a large river, we're looking at grid cells right now on an order of 25 meter by 25 meter, but that's totally dependent upon the grid resolution is completely dependent upon the model domain and the scale of the processes that you're interested in. These can be much smaller if needed, or larger if needed. So that's really dictated by the user needs as opposed to the model. The underlying tools can handle quite a broad range of grid resolutions and domain size. So this upper right panel here is showing the rating curve that we're applying at the downstream boundary. And then this stepped flow curve here essentially is the kind of the underlying driver behind this incremental flow, in-stream flow incremental method, where we're applying a series of fixed flows for a particular time long enough to reach steady state within the model domain. And then once we have achieved steady state, we extract the information from the model at various times toward the end of that steady flow period. And then that becomes the habitat value that we use in the analyses. So this is kind of a big picture overview of the domain that we're looking at. So now let's just jump right into looking at results from this model run. So we're looking at a particular species of Verba here as an example. And we're going to look at habitat suitability, or the habitat suitability criteria approach first. And here what we're looking at in these panels here are the suitability curves that are applicable specifically to the species and the life stage that you're looking at. And this little form here is just a data entry form, but on the right or the left column here under the x-axis, this is water depth. So under a range of water depths, you have an index that ranges from 0 to 1, and indicating 0 is essentially, not suitable at all, up to an index of 1, which is kind of ideal habitat. And then you have a range of fractional values of anything left between 0 and 1 in between. And then so this curve is the habitat suitability curve for water depth for Verba adult. And then similarly over here on the velocity parameter here, we can see that anything between essentially quiescent flow and just a word of note here with EEMS, it's assuming that if it sees velocities less than, or a parameter that's less than the low value, that it uses the same index associated with the lowest value entered. So a velocity of 0 would still have an index of 1. If you want to provide more detail, or if you don't think that's true for your application, then you can just provide more data points. You can add as many velocity or depth indexes and criteria as you need for your particular project. But in this case, velocities up to about 0.75 are ideal habitat. But once the velocities get up to about 1.5 meters per second, essentially not ideal habitat, so 0. So this is the habitat suitability curve shown here. Now, as I mentioned, for the extraction of the information for the IFIM method, we have to extract data results from the model at particular times. So this just is a summation of looking at the times and the associated flows that have been subsequently representative of the model results at that particular time. So this is the EEMS form where we fully describe a habitat analysis. for the, and then all this information for water depth and velocity, and you can have up to 5 parameters defining the criteria, the habitat suitability criteria for a particular species. And the drop down, the values available here are dependent upon what parameters are being simulated. So if I'm simulating sediment, for instance, I can add, total suspended solids here as a criteria, or I can look at dissolved oxygen if I'm simulating water quality, etc. And then this is the suitability curve, and I'll show you in the hands-on how to use it. Then you also have, because this can be a 3D or a 2D model, this particular model is a 3D model, we can actually extract data by layer, a particular layer, or a particular, or a range of layers representing a vertical variability, say, of velocity in the river or water body, or in the case of a value of 0, in this case, that's indicating a depth average. So essentially, the average vertical value is used for these criteria. And then you can post-process these data. This particular, if this box is checked, that means I can get a time series of my velocity. But anyways, that's the this information here. This criteria ID provides that unique connection between, you set all this stuff up that apply to a particular species and life stage, and then you can save it. Later, you can just load it back up and have access to all this information once it's defined. You can extract, once this has been set up, you can extract the habitat suitability criteria information from the model using this set of options and tools over here. You can specify the date range that you want to extract. By default, it will extract the entire model runtime. And then you generate the initial time series of extraction. And once that's done, down here under the secondary post-processing option, you have the range of different ways that you can then view and analyze the results from the extraction of the habitat suitability index. And then when you want to do, say, weighted usable area versus discharge, this is where that table of time versus discharge is entered, and then you can look at your data in different ways. So let's just look at the typical examples of output from the tool. So here we're looking at the weighted usable area generated for the Brabant adult stage under the range of different flow conditions. So you can see, the shape of the curve. So they kind of, if you will, the optimal flow for the Brabant and this particular stretch of river is somewhere around 800 or so cubic meters per second. So that's one way to look at this curve. Another way, and a very common way to look at this curve or these curves, is comparing different, say, project conditions. Say maybe the project before some dam was built or dam was removed, or some other habitat modifications to the watershed. And then you can do this and compare these curves, one curve to another, so you can see a quantitative benefit of the project or quantitative detriment of the project. So this is the same analyses, but we're just showing the composite habitat suitability index. So it starts off at a very low composite index for the entire domain. The highest that it ever gets to is approximately 0.7 8 or so, and then it begins as the flows increase, which, if you remember, they continuously increase, the suitability index decreases. So there's just another way to view the output. Another way to view the output is you can view the habitat suitability criteria in a 2D plan views from the model domain under a couple of any flow regime that you've simulated. You can animate these if you desire and save them out as ABI files, but this is under 2 flow regimes here. You can see the habitat suitability criteria is ranging from 0 to 1. So up here on the top panel at 500 cubic meters per second, you can see the distribution of the habitat suitability. But then down here under a higher flow condition, you see areas where it's beginning to lighten up, and that's areas of higher velocity, and so the fish find that area less comfortable, and so they exit that area, and that's why the criteria changes over time. So it just gives you a different way to view that same information. Now I'm going to go through these others a little faster to kind of use our time more wisely, but you got to understand the kind of the general layout now. So this is now looking at the critical limits analysis. This was what we were looking at earlier was the habitat suitability index and suitability curves, and numbers basically can range between 0 and 1 as far as what's suitable or not. A critical limits analysis is a little bit more cut and dried. It's going to look at, okay, what area or volume of water meets a criteria. You're either inside or you're outside. If any one criteria is outside these limits, then the whole cell or the whole layer, however you've defined it, is outside the limits, and it gets a value of 0. All these, the values all have to be between the min and max in order for a cell or a layer to get a value of 1. So this is just a binary 0-1 analysis. Very similar form for building up the criteria. And again, you can, once you've built all these, you can save them out. You can load them back in at any time, reprocess, or just immediately jump down and do secondary processing of those results. And this is the analysis from a critical limits analysis. We're using similar kind of criteria that were in the habitat suitability index, but here we're, again, it's just more the binary, meets the criteria or doesn't. So this again is the composite index. And here, just using that more simple approach, now let's just go back here to the suitable habitat volume and suitable area. You can see here that we're actually, much higher flows are still, quite suitable for this particular set of criteria, which, different. The 800 cubic meters per second occurs somewhere more in the day 213 to 214. So it's in this period of time here. So, just some of the differences between the curves and approaches. And then again, likewise with the habitat suitability criteria, you can also view the limits, habitat criteria limits, by 2D plan view. And again, this is just, a binary 0 or 1 or a on-off kind of approach. So here you can see everything that's in green is meeting the criteria at a flow rate of 500 cubic meters per second, and down here at 1,000, you have those areas of higher velocity now are outside the limit, and so they are just completely turned off for this critical limits analysis. So just I'm going to, again, just kind of scroll through just so you can see the different ways that, the different species are set up. So this is a different species. We can, again, you just set up your criteria however you want to set it up. This is for the juvenile species, juvenile muskellunge, then the fry, and then the difference in the weighted usable area between, for the same species, different life stages. So, the fry, like that more quiescent, slower water, shallower water, but as the flows increase, they like it less and less, whereas the juvenile and adult are, they like the deeper water up to, and higher flows up to a certain limit. So just different ways to look at these analyses. So again, 2D plan view for the habitat suitability criteria. And we've got the critical limits for the same species, and I'm not going to go into this much, again, detail, so we can wrap this up and get into the hands-on. So again, visualization, methodologies to view and extract time series and flow versus, index values, 2D plan views, 2D animations, etc. So with that, that concludes the presentation phase of the work. And before I move on to the next phase, I'm just on the hands-on, do we have any questions at this point that need to be addressed for the PowerPoint presentation phase?
If you have any questions, just feel free to type them into either the chat window or the Q&A. We'll just give people a minute to type those out.
Well, while you can go ahead and continue to type. I'm just going to go ahead and show while we're waiting on that, our website. So this is the primary website. You can get access to our resources here for the EE modeling system, and under the resources page, we can go to downloads, and we have our demonstration models are available to the user through the resources page. And you can download a host of different models, but including this habitat analysis tool or demonstration. So with that, let's go ahead. If there's no questions, we'll go ahead and just jump into the actual hands-on. So actually, I'm going to go ahead and exit this and rather show you how you load up a model to begin with, and then step through the model itself. So this is when you first start up EEMS 8.4, this is the main form. To bring a model into EEMS, you can click on any of either the browse button or the open button here, but most common way to do it that we oftentimes do, you just drag the folder that contains the model onto the main form here and loads the model. So that's just obviously a usability feature that keeps things moving quickly. And another very nice feature is if you want to open up another model, there is the history of up to 20 different projects that are available quickly to jump from model to model. And you can, once you've loaded the model, and you can go to the 2D plan view. That's what we were looking at with all these other views. You've got a host of different ways to look at the information. over here on the right panel, and then you've got a timing. You can slide around, look at different times, zoom in, turn grids on and off, bring in backgrounds, all kinds of typical visualization kinds of tools. So with this model set up, and if I were to save it and run it, I'll show you what that process looks like. So I have the model, I've created it, it's all ready to go. I'm going to go ahead and create a new folder, and I'm going to use one of my favorites, delete me, so that helps me remember to go back and delete that folder. So I just went out and wrote a new model to this folder. So if I come in here, you can see up here actually that this is under this particular folder for the habitat, then under model, and then delete me. So if I go into model, there's a delete me folder here, and this contains all the input files necessary to run the model. EEMS builds a complete data set. There's very few files that you ever have to directly edit unless you just want to. If you want to, you can, but EEMS will handle all the file creation for all the boundary conditions, all the domain, everything. Again, this is a huge time-saving tool. So with that, when I have it saved out, I can run the model, and I'll just show you. I won't run this model to its completion because it takes more time than I want to give it right now. But this is your typical runtime output. This is the results from a single cell in the model domain, and then it reports here how much time it estimates to take to the end of the simulation. So in my case, it's going to take quarter of an hour or so to fully run. We're using variable delta t, so this time step will change throughout the simulation based on the hydrodynamic requirements. So I'm going to go ahead and stop this for now, and then we'll stop it for now. You can pause, load the results, look at them, and then press another key to continue. Or if you press the same key, I press the lowercase y, if I press that same key again, it will exit the run. So I pressed lowercase y, model is finished, reports back how long it took to run the model and some other metrics which we won't get into right now. So with that, I'm going to go ahead and reload the model that we have fully run. And so there's an important kind of file structure here I want to mention. So all the input files necessary to run the EFDC model are located, and actually EEMS are located at the root level of a folder. The actual analysis and habitat analysis and the model output from at EFDC Plus are stored in different folders. So we keep your file structures well organized to help with file management and project management for your various projects. But in this particular case, since we're doing habitat analysis, and habitat analysis is available under the Model Analysis tab, which is where a lot of the post-processing tools are, including all our calibration tools and other things. We go here to the Habitat Analysis tab, and then we can do either the critical limits or the suitability analysis. So when we press either of these buttons, meaning that we want to do some habitat post-processing, EE will create this folder here, hashtag habitat. And in that, it will contain the various files, input and output files necessary for the habitat analysis. So let's just start off here with the critical limits time series. So this is what the form looks like when we initially load it. And in this particular model, the items that are available for analysis in our criteria are the bottom elevation, which probably doesn't change in a model unless you're simulating sediment transport with morphology turned on, which EFDC Plus can do. But typically, the bottom elevation may be used for things that if you've got a sloping bottom and you want only analysis of species in lower bottom elevation scenario, you can apply that if you want. But you also have water depth, bed shear stress, and velocity, and then also light penetration into the domain. These are all options that are available for this particular model. If I was simulating temperature, in addition to, let me close this actually and go here to the active module. So here's a list of all the parameters that are submodels that can be simulated using EEMS. So if any of these are turned on, then you can come over here to model analysis, and those outputs would be available to do the habitat analysis here in this drop-down list. I could go through here and manually build it up, and type in numbers and go to each one, give it a name, then generate my time series and save it. But I've already got these systems already set, or these habitat examples already set up, so I can just use the load button here, and here you'll see all the a listing of all the files that contain the habitat critical limits configuration for each of the different species and life stages. In this particular case, actually, and I don't know that I'll have time to look at it, but there's I'm also ran a comparison of looking at the juvenile muskellunge with just velocity and depth, and then what if I add a shear bottom shear criteria to that, and what impact that would have on the results. Probably won't get time for that, but this is how you would kind of organize your files. But let's just go ahead and load up the muskellunge juvenile here. As when I hit load, you can see here that it populated the ID, fully set up all of my criteria, and then I could, at this point in time, go ahead and generate at the initial extraction of all the EFDC model results that meet this criteria, and then from that, it would generate a range of different files that would be these here. When it says habitat results, with all these habitat results files here are all extractions from the original data, and then the original EFDC output. And then here, followed by habitat results, we have we have text that says, in this case, muskellunge adult, or down here, muskellunge juvenile. This text here exactly matches your criteria ID. And this is a way that EEMS can quickly link a criteria to an existing extraction. Because if you have a really large model and you have run these analyses over a long period of time, the extraction can take some time. So it's nice to be able to save out the extraction and quickly just jump straight to post-processing once you have generated the extraction. So in this case, that file here already exists, and the reason why this file is much larger is because you can do these extractions and get separate results on a cell-by-cell basis. And here we have 5,898 cells. So the file can be, fairly large. If I don't check this, then it's a composite index. I get one value for the entire domain, or one value for a subset of the domain. And that's what, if you wanted to do it only a portion of the model domain, you would use the subset here. But in this case, getting back to what we actually have extracted and ready for us, is the musculolung juvenile here. When I selected this, the secondary post-processing frame here is displayed. If this file does not exist with this exact name for this exact criteria, this frame won't be shown, because then you first have to extract it and then it's available. So once this file exists, you can immediately jump down here to any of these secondary post-processing numbers. And in this particular case, we're just going to look at the domain composite index. So remember, this is a 0 to 1 for each cell, but over the domain, you can have up to 5,898 0 to 1. So this is the composite index from that. And I'll load up that particular data file here. And it loaded the data for all 672 snapshots from the time series for these all 5,000 or nearly 6,000 cells. So this is what the composite index looks like for those criteria for that species for the and that life stage. So with that, I mean, we can load up. Well, I'm not. Excuse me, not save. I can load up a different, say for adult, and here again we have the velocity and water depth. It's already, well, actually in this case it hasn't been extracted. Let me load up one that has been. Well, I'll extract this for just a day. Say I only want to just extract for one day. 2011, 2010, 210. These are Julian days. They're essentially user-defined days. They can actually be a Julian day for a year, or they can be, any arbitrary day that user-defined. In this particular case, they represent the Julian day for the model, or for the year that we generated the original model for. But because this is a somewhat not arbitrary, but a user-defined flow regime that's not real, based on real flows, it's that step flow. It really, any number from 0 to 7 would have worked. But so with that selected, I'm going to turn off the cell by cell, generate the time series. Tells me how many cells meet the criteria. Since I haven't specified a subset, it's essentially all the cells. Tell it to proceed. Reports down here on the status bar what the time as it's extracting, and when it finishes, you get the information that you asked for. So here is the velocity. I asked for a series of the velocity. So that's why velocity is displayed on this panel here. And then just go here real quick to say velocity is red. So you can see the velocity over that 1 day period that we extracted, and the suitable habitat volume and area over here on the right axis, and then the time in Julian days along the bottom. So that's some of the ways that you can use the critical limits analysis. Now going on to the habitat suitability criteria. Again, it's the same process here. I can load up, but notice now we have a different set of files available. Actually, I forgot to mention this, but let me just jump back here and show you. So when you're loading a critical limits file, the extension is .hcl. So it just displays the files that meet the critical limits analysis approach. And then when you're doing the habitat suitability analysis, you get, it's the Hsc files. So in this case, again, we'll just pick the Muskellunge juvenile as an example. Now, this is the actual suitability curve. These are nothing more than the data pairs, followed by a semicolon for the ending the data pair, and then another data pair with. But if you just hit enter, it brings up the data entry tool. So as I change this, say actually, I want that 3 and or whatever, whoops, that to be 3 and this to be, say, 1, and then as the depths get really deep, 10 meters, it goes back to 0. They don't like deep water for some reason. This is an example. So as you just enter your information, you can see what that curve looks like to the right to make sure that it meets your expectations as to what you expect the suitability curve to look like for water depth for that particular species. When you're finished, you hit OK, and EE will rebuild this this line. You can type it into these directly if you want, but if you don't, just use the input tool. That's what more typically we use. Here's your layer options. You can see the tooltip when I put the cursor over it. These are the options that are available. I can extract a single layer, which in layers are the vertical discretization of the model domain. I forgot to mention this. This is, we're using 4 layers for this model. So let me load up the Muskellunge juvenile again. So I could extract, layer 1 through layer 4 individually, and then I can have a different velocity range for a different layer with a different set of criteria if I wanted to. But I can also extract a range or compute a value for a range of layers or an average of a range of layers, or just a 0 for depth average. So right now we're just demonstrating the depth average values. So with all this configured, notice that when I loaded the Muskellunge juvenile, I have a secondary post-processing option available. So here I can jump down to, say, the weighted usable area time series, and you can use this without the IFIM approach if you wanted to for a real domain. A real domain and a real flow regime. So you have a range of different a hydrograph, a storm event, whatever that you're simulating. You can generate the weighted usable area as a function of time. And I'm going to answer this. This question basically is allowing me to change my data that I'm going to display each time I select something over here. So the options are always, if I already have information loaded, I can just say yes to this, and it'll just plot and display and analyze the same data that you've already loaded. If I want to change it, I would say no to this question, which is, use the data already in memory. Then I can load up a new file. So here we're looking at the Hsc results. So here are the files that are output from the extraction process for the Muskellunge juvenile. And I'll just grab this file here, open it up. tells me that it loaded 672 snapshots that were output from the linkage files from EFTC Plus for nearly 6,000 cells. And this is what the weighted usable area is as a function of time for this for the muscle lung juvenile. I can also then look at it as a function of discharge using this curve here, which we've entered and it's saved, so you don't only have to enter this one time during your analysis. And then I can generate weighted usable area versus discharge. Whoops, actually, just use the same data. So this is the weighted usable area as a function of discharge. And this discharge is a function of that stepped hydrograph that we used for defining the flow regime. So I could go through, we can do other species and examples, but I think you get the basic idea here. So let's jump over to visualizing the same data in a different way in the 2D plan view. So I'm going to go ahead and cancel this, jump back out here to the view plan or the 2D plan view option here. Make it bigger, change scale. You've got access. So I right mouse clicked on the scale or the legend. It brings up display options. I can come up here and do the same thing with the toolbar and bring up the display options. Then there's a lot of different options that are available. Turn on and off scales, change units, add north arrows, put grid, overlay a grid on the domain, etc. Change to calendar dates if I actually, if it was a real model application with flows that are actually based on a measured data, then a lot of times it's nice to be able to display it as an actual date instead of just the Julian time. But we're leaving that alone for now. These boxes here are what are known as timing frames. And what you can do, the idea with these boxes is they show the user kind of a relative effect forcing. So as, say, in this case, this is the upstream flow, you can see that, the flow is stepping up and initially it's quite low. So if we come over here and look at, say, water levels, initially it's quite essentially nearly a series of puddles in this initial condition. But once we run it out here, just a few hours into the simulation, you can see now what the depths are over time at that particular flow rate. And then I can also jump out here by just right mouse clicking somewhere on the timing frame and go to that time and see a different set of flows. So now we're looking at depths up to 4.5 meters, etc. So this is the interface for the 2D view, and you have access to a lot of different ways to look at the information that is stored. And again, this viewing options grows and shrinks based on what you're simulating. If you're simulating temperature and water quality, it would be added up here to your range of options. But for now, what we want to do is just look at habitat index. So to do that, if I hit F2, it shows me a list of all my keystrokes and shortcuts. And the one that we're actually interested in right now is Alt-H for the habitat analysis. So with this, I can hit Alt-H and bring up the range of options. One of those that we haven't really discussed because it's not a new feature, but we have the thermal and depth criteria limits, which was uniquely designed originally to address manatee habitat because they have to have a certain depth, and because it's changes with time, with the tide. We have, there's some timing issues around that, and that's all, and we won't get into that right now, but what we can do and what we will do right now is look at the critical limits and the habitat suitability indices. So if I go to, say, critical limits and pick the Muscalong fry here as an example, it opened. Now remember, this is yes or no. So this is a binary, meets the criteria or doesn't meet the criteria. And then, so the gray here has the index is 0 as I click on it, and then over here the index is 1. So these areas that are shown in green, the fry like these areas, whereas the areas that are white, these are islands in the middle of the river, and they're dry all the time. But these, as I click on these, you can see there's depth of water of 1.5 meters roughly out in here, but over in here it's under 1 meter. So anyways, the fry like these areas and don't like these areas. And then you can change under different flow regimes. You can see how it changes. Or you can go back to, I can also press Control G and go to a particular time, say 2:10 noontime on day 210, and these really low flow conditions, as we mentioned in the presentation, the fry like those conditions. And the higher flow, too much velocity, too much depth. So with that, one way to look at it, we can also then change. By the way, if I click on, I can either switch off habitat suitability criteria over here, or if I switch over here, any of these parameters on the viewing options, it automatically turns off the habitat tool. So to turn back on the habitat tool, I just, again, Alt-H, select the tool. Now we're going to do the habitat suitability indices. And again, I'll pick the, well, let's pick the juvenile in this case. So here's the juvenile, and now the gray areas at this particular time are dry. Right now, in this case, these big, white blobs are the islands, and then these areas that are near white around the edges of the greens, this gradation of white to dark green, these are areas that meet, are somewhat inside the criteria, but they're quite low. So if I click on a cell here, it's the suitability index is nearly 0. If I click on a cell out here in the middle, it's very, very good. You can, again, just like with the critical limits, I can jump to any particular time, see it, or I can turn on the animation tool and display the data as it changes in time. So here it's clicking through the time. Let me speed that up a little bit. And then once this, I'll just let this run, and then we can go ahead and start to get some, move on to the question and answer stage. Because at this point in time, I'd like to transition to Q&A, and pretty much any topic on EEMS, not just the habitat tools. We can discuss if you have a question, but you can see as it's animating through time, you can see what's happening over here to the flow regime and the time, and as the habitat changes rapidly at various times. So yeah, this is a typical analysis for the habitat suitability criteria. So with that, I will now stop, and we can enter the Q&A session. So if you have any questions, You can either type them or you can raise your hand if you feel comfortable. You're welcome to ask them verbally, but otherwise just let Tom know.
Great. We have a question, Paul.
Okay.
Yeah, so how many criteria can be added for HSI analysis, including water quality variables? In addition to spatial aggregation, can HSI be calculated for criteria over temporally aggregated periods, i.e. several days, monthly moving averages, etc.?
Yes. Good point. And well, up to right now, the way we've got it configured is that you can only include in the criteria up to 5 of the parameters. You might have, say, water quality to do a typical eutrophication simulation in EFDC Plus. You've got to simulate at least one algal class and your organic, your carbon content, your phosphorus family, your nitrogen family. So it takes somewhere, for a full eutrophication model, it takes somewhere around 14, minimum of 14 parameters. So you probably you can't include all of those in, say, in one of these analyses. You can include up to 5, and so you would pick in this. Typically, it would be like dissolved oxygen and temperature and, say, depth and velocity. But maybe your dissolved oxygen, you're not interested in the depth average values. You're really interested in, the dissolved oxygen at the, near the bottom of the domain. So you can select the layer range. I want to go from, the bottom to up to, halfway into the water column, as an example. But you can only have 5 right now. There's a need for more. You can always just let us know, contact us, and we can discuss with you either a custom version, or we can look to add it to the list of future capabilities as we continuously improve the tools. We could add more criteria. Now, as far as the temporal blocks, there's a couple of ways that can be done. If you're trying to if you want to do one large extraction over the entire simulation period and then look at running averages or block averages, those capabilities are part of the post-processing tools that are available with EEMS. So I would extract, say, a full 7-day period in this particular example, but then I could go back and post-process these data into daily blocks or into 3-day blocks. I didn't, we don't have time to do it, but we have an example where we were looking at the Lower St. John's waterway in Florida, looking at habitat analysis for basically freshwater wetlands along the shorelines of the Lower St. John's waterway. And we use this tool to say, okay, it must be the maximum depth can't be over, I think it was like 1.5 meters in a tide cycle, and the salinities had to be under 2 ppt, and then they were interested in 30-day, 90-day, and it was like a 30-day and 90-day blocks averages, and looking at the cells along the shoreline and in the wetlands that met those criteria in short-term acute daily values, and then these longer-term block averages, and looking at them over time, so you could pick critical periods, like a 90-day critical period for a particular region of the wetlands. So those types of analysis are available with these tools. Did that answer the question? Or maybe too much?
Yeah, I believe you addressed it. If you have any follow-up questions, George, please feel free to type them into the chat or into the Q&A box.
Okay. Sorry, I had to drop off. Things are back now, so just wanted to say thank you for your participation and be happy to answer any questions that you may have, either emailing the info at EE Modeling Systems or Hannah or myself, Tom, Janesh, any of us. We'll be happy to communicate. But again, appreciate your time.